So you should just have seen something popping up on your screen saying the session is being recorded. Did you see that? Raise your hand if you did. Okay, so that worked. Good. So you're going to be knowing, you will know when I'm recording because that will pop up, unless you come in before it's in. That's good. Y'all can lower your hands again. Now, the reason we want to use complex numbers in polar form is because it helps us with multiplication and division, and with taking powers too. Yeah? And when I mean taking powers, I mean bringing up like squaring and cubing and stuff like that, but I also mean taking roots. And we're going to talk about how to do that today too. Today I'm going to be using two numbers, two complex numbers, which are easy to work with because they both track back to some of our principal angles. Okay? Z in here is going to be root 3 minus I. And I've plotted this on the Cartesian plane. Okay? I've plotted this on the Cartesian plane. I need to keep that chat thing open so that I can look up and see if anybody has said anything too. Okay, so this is on the Cartesian plane. And here, Z here is given as root 3 minus I. And that means its coordinates are root 3, negative 1. W here is 2 plus 2I, and its coordinates are 2, 2. This is on the complex plane. Real axis, horizontal. This is the real axis. And this is the imaginary axis. And you can read the coordinates off on that, right? Now, when we're looking at Cartesian, just the x, y coordinates, they're easy to add, subtract, and scale. Because you just do it coordinate-wise. Add the real to the real, the imaginary to the imaginary. If we're scaling, just multiply everything by a constant. That's all there is to it. Okay? But if we want to multiply and divide, there's a better way. You can multiply and divide, using your distributive law. Yeah. And long division. And that's kind of awkward. So it's actually better to use polar form. And by polar form, I could mean one of two things. Mostly, I mean the r cis theta form. Okay? But r cis theta implies r theta, which is polar form. So the actual polar form is r theta, as versus x, y. Okay? And I want to show you how this works. Okay? So z here is root 3 minus I. Okay? That corresponds to x and y coordinates of root 3 and negative 1. Now, the length of that vector, root 3 and negative 1, is 2. Just square the two pieces, add them, and take the square root. You get 2. And then to figure out the angle, you take the arctangent of the y coordinate divided by the x coordinate. Now remember the arctangent, the principal arctangent on your calculator returns results in, remember the arctan goes along with the sine, which is a y thing, and so the value is from negative pi over 2 to pi over 2. Because arctan goes along with arcsine, and sine is a y thing. So that's the values. So the arctan on your calculator does not cover things in the second or third quadrant. But you can see that. If it's in the second or third quadrant, then the x value will be negative. And if the x value is negative, just add pi. That's all you have to do, or 180 degrees. To keep things simple, I'm just keeping it with degrees right now. Now, negative 1 over root 3, I think of its reference angle. The reference angle is 1 over root 3 is going to be 30 degrees. The fact that we're at negative 1 over root 3 means we're in the bottom half. Quadrant 4, negative 30 degrees. So in that sense, we can change this to 2 cis negative 30 degrees, where cis is my shortening of cosine theta plus I sine theta. So it comes out as 2 cis negative 30, or 2 negative 30. For W, I would calculate the radius, the length of the vector, as the squares of the coordinates, 4 plus 4, give me 8. And I'm going to take the square root of 8. I'm going to find myself at 2 root 2. Now, for 2, 2, that's pretty obvious, isn't it? If I'm going from here up to 2, 2, that's got to be 45 degrees. Yeah? That's pretty obvious. And like I said, you can do that by inspection. The other one, you can actually plug it into your calculator, 1 over root 3. But that's a ratio you should recognize as a principal ratio, associated with a principal reference angle of 30 degrees. And from there, you'll decide whether you have to add or make it positive or negative, or whether you have to add 180 to that to finish it up. But there you are, okay? So, our z now is root 3 minus I. And our w is 2 plus 2i. And now here comes the fun part, okay? We also know that z is, let me set this up nice, there we go. Yeah. I've got the chat tab open, and I'll look up at from time to time, so I'll see your comments there, I hope, okay? So we know this is 2 cis theta, and I'll write it all the way out this time. This is 2 cosine theta minus 2 sine theta times I, and that's exactly what we mean by 2 cis theta. Right? And I'm sorry, but I'm writing theta. We know what theta is. Theta is negative 9 degrees. 2 cis negative 30 degrees. And over here we have 2 root 2 cis 45 degrees. Now the thing to keep in mind here is the argument, the angle theta and the cis. By way of the Euler identity, this is an exponent. I should do that in a different color. And this is a scalar. Yeah. And what do you do with exponents when you multiply? When we multiply, what do we do with exponents? Anybody? Go ahead and speak up. Okay, well, make sure that we're clear on that. Okay. When I say 2 cis negative 30 degrees, I mean 2 e to the I negative 30 degrees. That negative 30 degrees is an exponent. And I write 30 degrees, negative 30 degrees, but you can't use degrees in exponent. You'd have to turn it back to a regular number, which means you'd have to translate that to radians. And you translate to radians by multiplying by pi over 180. But still, as long as I understand it's not in its normal units, I can keep on working with it. As long as I remember that I have to, if I was going to do actual calculations with the exponent, I have to bring it back to radians. I can still work with it untranslated. Okay? And I'm going to multiply this by 2 root 2 cis 45 degrees. Now, what do we do with exponents when we're multiplying? We just add them. That's right, Ryan. So let's do that. So here's where we're at. We're looking at 2 negative 30 times 2 root 2, 45. And now I'm taking all the way back to r theta form. Okay? And to do this, we're going to multiply the scalars. And then we're going to add the exponents. And let me write that cleaner. Add exponents. Okay? So that really is just as easy as you think, right? Another example. 3 17 degrees times 5 negative 22 degrees equals 15. And then what do we do with exponents? We add them. 7, that's negative 5 degrees. Just like that in r theta form. No, I don't want that color. But remember that 317 means 3 cis 17 degrees. And 3 cis 17 degrees means 3 times e to the I 17 degrees. Okay. Let's talk about dividing. Okay? And so I'm going to divide now. Again, z is still just what it was, right? Right? And w is still what it was. Right? Now, this time we're going to divide. What do we do? What do we do when we're dividing exponents? What do we do to exponents when we divide? Anybody? Ryan? That's right, subtract, subtract. Everybody knows that. That's good. Okay? So, if I multiply the scalars, I get 2 times 2 root 2, right? But now I'm going to divide the scalars. Dividing the scalars gives me 1 over root 2, yeah? Also sometimes written as root 2 over 2, right? But you can see it. That's 2 divided by 2 root 2, right? And now for the angle, we're going to get negative 75 degrees, okay? So to divide, you can divide the scalars. And, yeah, let me center that this side. There we go. Divide the scalars, and then we subtract the exponents. Obviously, z times w is the same thing as w times z, right? But we can figure out what w divided by z is as well, right? And here, now, I'm going to write this again up here. This is in the form 2 negative 30 and 2 root 2 45, right? Except now I'm going to move w up top so that I can see what I'm doing. W is 2 root 2 45 degrees. So w divided by z is going to be root 2, comma, and I'm going to subtract. It's 45 minus negative 30. $75 degrees. Which we could also write, yes, is root 2 cis 75 degrees. And this is actually the way I prefer, because the coordinates are okay, but if you write it as a cis, you'll remember that the cis is an exponent. It gets blurry sometimes, I know, but hopefully it's only blurry for a second or so, and then it resolves. And if it doesn't, again, I know you've been having lots of connection problems today. This part I'm recording. Okay. So does that seem pretty easy, guys? Because it is. And think about this. This is the alternative. This is the alternative to multiplying using distributive law. And it still works the same way, right? Yeah? Let's multiply z times w. Just we'll use the distributive law. Okay? So we had z, which was root 3 minus I, and w, which was 2 plus 2i. Let's multiply those. So that gives me, well, underneath, because I don't want to do it there. That would give me z times w equals 2 root 3 plus 2 root 3 I minus 2i minus 2i squared, that's plus 2. So I'm seeing 2 plus 2 root 3 and the other one is 2 root 3 minus 2. I. Okay? I would need to figure out what the cosine and sine of 15 degrees is in order to make that work out. And I could do that. Using the sum and difference formulas. I'm not going to get that quite that brave, but I could show you how to do that, right? Okay. Let's say that we're trying to find the sum or difference of 15 degrees, right? 15 degrees, we can see this is from principles, yeah? And cosine. Okay. Cosine 15 degrees. Now remember that's 45 minus 30, right? Right? And cosine is CC minus SS. Okay? We're going to let the theta be 45 and the phi be negative 30. And so I get cosine 45, cosine negative 30, which is the same thing as positive 30, minus sine 45, sine negative 30, but I'll make that positive because it's negative 30. Okay, the cosine of 45, root 2 over 2. The sine of 45 is also root 2 over 2. The sine of 30 is 1/2. The cosine of 30 is root 3 over 2. So that's root 6 plus root 2 over 4. Now, I'm just going to do this for cos. I'm going to take this times 4 root 2. Okay? If I multiply this by 4 root 2 from the r, remember I'm just doing the x coordinate now. I'd have to do this for the y coordinate as well. 4 times root 6 plus root 2 over 4 looks like root 12 plus 2, and root 12, because the 4's cancel, yeah? And root 2 times root 6 plus root 2 is root 12 plus root 4, which is 2. And that number is 2 root 3 plus 2, which is the same thing as the x coordinate. For z times w. And I think you can see pretty easily that that was just awkward, 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 right? So we want to use cis as much as we can. And we'll translate back to rectangular only when we need to. All right? So now we can go to de Moivre's theorem. De Moivre's theorem is how to do powers. So let me clean that up. And the idea is fairly simple here. Okay? Let's say that I wanted to find z cubed. Okay? Notice this is going to be z times z times z, yeah? 2 cis negative 30 degrees, 2 cis negative 30 degrees, 2 cis negative 30 degrees. We're going to multiply all these. So, what's 2 times 2 times 2? 8, right? Yeah. And now remember the rest of its exponents, right? What's negative 30 times negative 30 plus negative 30 plus negative 30? Negative 90, huh? Negative 90, yeah? Negative 30 plus negative 30 plus negative 30 is negative 90, right? What's the cosine of negative 90? And what's the sine of negative 90? I think everybody should know the cosine of negative 90 is 0. It's the same thing as the cosine of positive 90. Yeah? This is 0. And what's the sine of negative 90? Negative 1, yeah? So this says this should be negative 8i. Okay? In general, if we're going to take the power of z, get this squared away and then freeze it. Z to the n is going to be the r part, that's the scalar, r to the n, right? Yeah? Times cis n theta. Okay, and you just saw that happen, right? With z cubed. But because this is coming from exponent rules, we're not stuck. And de Moivre's theorem only works with integer powers. It's only for integer powers. And this is de Moivre's theorem. And as I said, de Moivre's theorem is really only, punching the wrong buttons here. De Moivre's theorem is only for integer powers. But the point is, if we take this back to the Euler theorem that it's based upon, and remember to change, note, n can be any number. Okay? And that would work. That can work. Not just integers. It gets a little more complicated if we're not using integers. Because you can have, for example, let's talk about just taking roots. We talk about roots. Well, then things get really complicated because instead of calculating just the power of n, and there's only one possible power, we'd have to be talking about taking the root, and we always know there's n possible roots. And that's the toughest part of the entire presentation. Okay? This is for powers I just did. So let's talk about taking roots. So this is easy if you do it methodically, but you have to do it very methodically, or you lose track where you're at. So here's the idea. Let's say z was root 3 minus I. By the way, I could have cubed that. I should have done that. And we got time for that, so I'm going to do that. Okay? I'm going to cube root 3 minus I. Now there's a formula for the cube, and we'll actually talk about this formula, the binomial theorem. And the binomial theorem starts out with 1, 3, 3, and 1, because those are the numbers off of Pascal's triangle. Those are my coefficients. Okay? And then I'm going to back that up with root 3 cubed, then root 3 squared, and then root 3, and then nothing. And then I'm going to have negative 1 cubed. Nope, negative 1 to the 0, sorry. Got ahead of myself there. Negative 1 to the first, negative 1 squared, and negative 1 cubed. And that's how you do this. Okay? This is obviously meaningless, and this is 3 root 3. Root 3 times root 3 times root 3. This is sorry. I was writing negative 1 when I should have been writing negative I. There we go. And so this is 3 root 3 squared is 3 times 3 is 9. 9 times negative I. And then we get what? 3 times root 3 times negative I squared. Well, negative I squared is just negative 1. And so that's negative 3 root 3. Now, negative I cubed is negative I cubed. Right? And I cubed is negative I, so it's positive I. So this is plus I. So these two cancel, and these two add up to, surprise, surprise, negative 8I. Same number. But to get the cube using de Moivre's theorem, it was just, 2 cubed times negative 30 times 3. That's all the calculation you had to do. If I want to do it longhand like this, multiplying it out, that's more awkward. So if I do it in Cartesian or standard form, it's much more awkward than polar. And that's the case anytime you're multiplying or dividing or taking powers. So, taking powers includes taking roots. So let's figure that out. The first thing I want to do, because this is always the example that everyone uses, is I want to find roots of 1. And this time I'm going to use a different z, and I want to find the cube roots of 1. Now this is a polynomial, right? This is a polynomial equation, yeah? Z cubed equals 1, right? This is equivalent to z cubed minus 1 equals 0, right? Yeah. This is equivalent to z cubed minus 1 equals 0. And as a polynomial, we know that has 3 roots, right? If I include the complex roots. What's really nice about this case is that we can visualize these solutions really nicely on the complex plane. Everyone here should be able to find one cube root of z, the first cube root of z, yeah? Who can tell me what the cube root of 1 is? Yep. That's easy, huh? Okay. So I'm going to show you how that works. There we go. This is the unit circle on the complex plane. And everybody tells me that the cube root of 1 is just 1. Yeah? Now, to find the other 3 cube roots, okay? And again, this is 1, and I'm going to call it 1 360 degrees so you can see it. That's in polar form. Okay? Now, cube root is what power? Cube root is what power? Anybody? Okay. 1/3. That's right, 1/3. Yeah, 3 is for cubing. Cube root is 1/3. Yeah, that's right, that's right. Okay? Now, and remember for powers here, yeah, we'll take 1 to whatever power is always 1, right? But what's 1/3 of 360 degrees? Because with the cis part, the theta part, we multiply. Okay? Kind of like we were adding when we're adding exponents. We add exponents when we're multiplying, but when we're taking powers, we multiply by the power. What's 1/3 of 360? 120 degrees, right? Now, if I cube that 120, cube the 120, right? This is just cis 120. If I cube cis 120, I'll get cis 360. Back to 1, right? And there's another root down here too. At 1, 240, which is cis 240. Okay? If I cube cis 240, and I need to put the parentheses around the whole expression. Is cis 3 times 240? 3 times 240? 720, right? And same way as cis of 360, cubed is cis 1080, right? But the thing is, all of those are equal to 1. Because those are all the same thing as cis 0. Because every 360 degrees, you're right back to where you started with in polar coordinates. And that's the trick. Let's do the next obvious example. Square roots. Z squared equals 1. Square roots of 1. Okay? Now I'm going to remind you, zoom this in, I'm going to remind you that this is equivalent to z squared minus 1 equals 0, right? Yeah? Everybody see that? Yeah? I bet you can factor that, can't you? That factors as z plus 1 times z minus 1 equals 0, and it gives you the solution z equals plus or minus 1, yeah? Now, let's look at that in the complex plane. we go. That was an awful circle. That was better. Okay, so once again, let's start here at 1 on the complex plane. And hopefully I can stop making this go around. Here we go. At 1, 360 degrees. What you're thinking of now is cis 360. Okay? I can do this with radians and call it 2 pi. Same thing happens, okay? Now, if I take this to the 1/2 power, then I'm going to be here, aren't I? At cis 180. One 180 degrees, or cis 180. Now remember, this is the real axis, and this is the imaginary axis. This is distance 1 from the origin. This is the number 1. This is the distance -1 also, but go the other direction. That's the number -1. Real numbers. And we got there the same way as we did. And we got there the same way as we did using the unit circle and cutting it in half. I don't like to start with that example because in the other example, you can see exactly what's happening here. You're finding the solutions are spokes on a wheel. So the solutions are spokes on a wheel. Let's do that naively and then we'll prove it. For z to the 4th. And then for z to the 5th. Okay? And I've got about 10 minutes left. First, I'm going to look at z to the 4th. So I'm going to try to find the 4 fourth roots of z, which means solving z to the 4th equals 1. Okay? And I know this is the same thing as the polynomial z to the 4th minus 1 is equal to 0, which factors z squared plus 1, z squared minus 1, and this one gives the solutions 1 and -1, and this one gives the solutions I and -I. So I could totally do this just by factoring. Okay? But now I'm going to forget that. I'm going to totally forget that. And then I'm just going to look at the wheel. Again, this is the complex plane. Here's the real axis. Here's the imaginary axis. And what I'm going to do is I'm going to grab one solution here, and now I'm going to cut the circle into 4 equal pieces. If this is cis 360, 1/4 of that is going to be cis 90. This is I. 2/4 is going to be cis 180. That's -1. 3/4. Oh, I thought I had that frozen, sorry. 3/4 is going to be here at cis 270, which is -I. And there you can see the 4 spokes on the wheel that represent the 4 fourth roots of 1. because that's how it works. What's 1/5? What's 1/5 of 360 degrees? That's where we're going next. One-fifth of 360 degrees. Remember, 360 degrees was part of a numerical convention, a base 60 convention, that was actually constructed to make sure that you would be able to divide by 5. So 1/5. Had to crank up my air conditioner. So 1/5 should be 120, 72. That's right. That's right. Thank you, milady. Okay. And so here I'm going to start my little circly thing again. And now we're going to use that to just eyeball where the solutions are. 72 is what? That's more than 60, less than 90, right? So here's one of the solutions. Cis 72 degrees. Okay? And as soon as you got that first one, you just start taking multiples till you get back to 360, and those are going to be the solutions. Those are going to be the solutions, okay? Yeah. So cis 72, and I also got cis negative 72 down here. But we'll get there. Cis negative 72 is going to be the same thing as 4 times 72. And that's 1/5. And then 2/5 on the cis 144 degrees. Now 144 is like 135 plus a little bit, right? And 135 is right there, and so it's going to be more than that. There's cis 144. And then we'll add 72 to that and find another spoke here at 216, right? Okay, so does everybody see where I'm getting these numbers from? The 72, the 144, the 216? And the negative 72 is, well, let's go ahead and add 72 again, 288, yeah? But I think you'll notice that 288 is 360 minus 72. Yeah? And let me zoom in just on our little piece of the picture again. There we go. All right, so that's where all the things are. And I have my original solution here at 1, which I'm actually thinking of as cis 360 because that helps. I consider it cis 0, but it's easier to divide 360 by 5 and get things. But in any case, though, there are the spokes on the wheel. Those are the 5th roots. And this is always going to happen like that. You'll have 2 spokes, 1 and negative 1 for z squared, and then 3 spokes, and then 4 spokes for z to the 4th, and 5 spokes for z to the 5th, and that takes you there. Now here's the real fun part, guys. What we're going to do, as soon as we have any solution, and I'm running out of time too, so I'm not going to be able to finish today, because I have to finish before your next class, guys, because it feels like I could go forever because I've got you here, and no, other classes still are going to have their time. So that's what's going to happen on that. Okay, but this right here is the basis on how we're going to do the other ones. I'm going to show you how to do the other ones on a fairly simple example with W. I'm going to take the 4 fourth roots. I'm going to find the 4 fourth roots of W here. So I'm going to say z to the 4th now, my new z. Okay, there we are. Now here's how we do this. Here's how we do this. I'm going to take 1 4th root of this. Okay? I'm going to take 1 4th root. And the 4th root of 2 root 2, well, let's make that root 8 again. Okay? And the 4th root is, remember that's index 2, yeah? The 4th root is going to be the 8th root of 8. Okay? I should have done that in a different color. And now here's the fun part, guys. What's 1/4 of 45 degrees? 11.2? Is that what you get? 1/4 of 11 of 45? Yeah? Okay. That's good. And now here, that's one of the 4th roots of W. That's one of them. You know how we find the other ones? And this is really cool. I'll call that Z1 because it's one of the 4th roots. I'm going to multiply this one by cis 0, which means multiply by nothing. Just leave it as it is. And now I'm going to take the rest of the solutions by remembering that what 1/4 of 360 is 90 degrees, and I'm just going to start adding that. So I got my solutions are Z1 is just the 8th root of 8 times cis 11.2 degrees. The second one is going to be the 8th root of 8 times add 90. Add 90. And the third, 8th root of 8, add another 90. And the fourth, add another 90. And hopefully I didn't mess up my arithmetic at all. Okay? Here's what you had. There's Z1. This is Z1 times cis 90. Because if I take Z1 to the 4th, I get the number. And if I take cis 90 to the 4th, I get the number. And so if I multiply the two, Z1 and cis 90 to the 4th is going to be my number, W. And the same is going to be true for Z1 times cis 180, which just means add 180. And Z1 times cis 270, just add another 90. Because the idea here is that all of these, cis 0 to the 4th is 1, cis 90 to the 4th is 1, cis 180 to the 4th is 1. And so multiplying each of these, taking each of these to the 4th power and multiplying it in, doesn't change the fact that it's a solution. And that's the trick on calculating this. And I'm out of time, and so I'm going to stop my recording.